Hi, welcome back to the channel. Today we're going to be talking about related rates, which are a topic typically encountered in Calculus 1 and that typically give students fits and night terrors, but really they're not such a bad topic at all. So we're going to look at a related rates problem, read it, talk about how to solve it, and then we're going to solve it. So really the goal of this video is just to show you that related rates are not so bad after all. So we've got this problem in front of us. It's a big word problem. I think perhaps one of the reasons students are so scared of related rates is because of how big the problems are. But let's just read it step by step and take in each piece of information we need. So the problem reads, the weight of a space shuttle above the moon is given by the function, and we have this function right here, W would be the weight, equals W naught times parentheses 1080 divided by 1080 plus h squared, where W naught is the shuttle's weight on the surface of the moon, and h is the shuttle's height in miles above the moon's surface. Then the problem reads, if the shuttle weighs 450,000 pounds on the moon's surface and is traveling away from the moon at a rate of 5 miles a second, what is the rate of change in its weight when it is 20 miles above the moon's surface? So basically, what I want to convey to you in this video is that related rates really are nothing but the chain rule. So first I'm going to talk about the chain rule, and then I'm going to explain how this is basically going to solve every related rates problem you're going to deal with. So the chain rule comes from the idea of composition of functions. So a function, we'll think of it as f, is something which associates an object in a domain to an object in a range. This is in very simple terms, but this is what a function is. But then we can take another function, for example, and do what's called a composition. And here, after a composition of functions, the object in the range of the first function becomes an object in the domain of a second function, which has, of course, g of f of x as an output. But we can still think of this whole thing as a single function which takes something x to something g of f of x, right? And so we can think of this all as one function. And we can still find out what the derivative of this whole new function is in terms of the derivatives of this function and this function. And the rule for that is g of f of x, and by prime here I mean derivative, is equal to g prime of f of x times f prime of x. So the derivative of this g function with respect to this variable times the derivative of this f function with respect to just x. And now here's why this is going to solve all of our problems in the case of the chain rule. It's going to solve all of our, in the case of related rates. It's going to solve all of our problems in the case of related rates, because all we're doing here in related rates is we're having our dependent variable be t, time, right? And that's going to map to something else, right? In our case, we're going to have some h function, which will be the height above the moon in terms of time, h of t. And then we're going to get our weight function from height. That's why this problem looks a little tricky at first, because we're hiding the fact that this h is really a function h of t. So what we're spitting out here in this w is really w of h of t, and then the related rates part, or the chain rule part, solves the related rates part because what is it asking, right? It's asking for the rate of change in its weight. Forget about the rest of it for now, when its height is blah, 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 blah. But the rate of change in the weight, well, what is that? Well, weight is a function of time, and rate of change means derivative with respect to time. So it's asking us W of h of t prime, just like over here. And that's going to be W prime of h of t times dh dt, another notation for derivative with respect to time, dh dt. Okay? And now you can see that we basically have all that we need to solve this problem with these blue numbers here up in the problem. We just have to figure out where we plug each of them in, right? So first of all, W prime of h of t, well, this is right here basically W of h of t. So taking the derivative of this with respect to h will be taking the first part of this formula right here. So let's just continue our math, and we would get that dw dh, which is another way of writing this, times dh dt, and this part is going to come out to, so we take down an exponent here, 2 w naught, right? We'll plug w naught in later, times, and then the exponent here goes down to 1, so we get 1080 over 1080 plus h. And then we have to use the chain rule on this one and multiply by the derivative of the inside of this exponent, which we can get using the quotient rule. So the quotient rule is that it's the bottom times the derivative of the top, which in this case is 0, so we can ignore that first part, minus the top times the derivative of the bottom, so minus the top, which is 1080, times the derivative of the bottom, and the derivative of the bottom, as you can see, is 1. And then that's all divided by the bottom squared. All right, if you don't remember the quotient rule, it's a good time to review it because you'll need to know it if you want to pass the class that you're in. And then all times dh dt. And now I claim that we have everything we need to solve the problem, spit out a number, because what is W naught? Well, we know the weight of the shuttle on the moon's surface is 450,000 pounds. So W naught equals 450,000. Next up, what is H? H is right here. When it is 20 miles above the moon's surface, so H equals 20. And then it is moving away from the moon's surface at a rate of 5 miles a second. So that's going to give us our dh dt. dh dt equals 5. And that's going to be plus 5, right, because the height is increasing. Okay, and then we just simply plug in. So what do we get? We get that it is 2 times 450,000 times, and then we can plug in here, and we get 1080 over 1100, right? Because 1080 plus 20 is 1100. And then we get times minus 1080 over 1100 squared times 5. So let's do out some math a little bit. So this 2, this 5 together make 10. So this is now going to be 4,500,000 because of this, obviously. And let's take one of these 1100s because we have an extra one, right? We have 3 of them and only 2 of these 1080s, so we'll just put one of them right here. And then let's clean this up as much as we can. 1080 over 1100 will reduce. You can check this. It turns out it reduces to 54 over 55. And like I said, there were 2 of those each left. So squared. And then we can just plug this into our calculator. Oh, and there should of course be a minus sign out in front. Don't lose track of that minus sign. And we plug it into our calculator and we get that it comes out to minus 3,940 pounds per second. So this is how we do the problem. To review, we start off by basically applying the chain rule. Related rates problems are just chain rule problems where the dependent variable is time. So we have this function w, and it's given to us in terms of h. And h is given to us as a function of t. So really w is a function of t, so when we take the derivative, it should follow this rule from the chain rule. Then we do it symbolically, and we go back to the problem and find that we can basically plug everything in. And after we do some creative cancellation and plug into our calculator, this is what we're going to get. So I hope that was helpful. Don't fear related rates. They are just the chain rule. Through understanding the chain rule, you shall understand related rates. Have a good day.